Hi, this is Mr. Ziegler here. I'm going to walk through Thursday's assignment, which is Charles's notes and simulation. So when I open it up here, I should have a slideshow once it loads here. Oh, here we go. I have a slideshow. And underneath here, when I click on this, I'm going to get a worksheet that pops up here. I'm going to kind of split screen this so I can see both the slideshow and the notes at once. And I'm going to follow my worksheet here. Here we go. All right, so first I need to watch this demonstration. And let me move my head up here. And then we need to use particulate drawings, which are dots and arrows, to describe what's happening with the gas molecules inside the bar of soap. All right, so let's watch this demo.
And what I've done is you could just put the whole thing in there, but I've cut it into pieces, so I want a little bit more surface area. All right. So now we're gonna put it in the microwave, and we're gonna put it in there for about I don't know, maybe 80 seconds, minute and a half, somewhere around there. I don't know. Okay, go. So it's just gonna cook away in there. All right. Okay. So the camera can kind of cut away and do this every once in a while. It's just gonna have to work here for just a second. We'll get back to it.
All right.
Ivory is a special kind of soap. Here, watch this. Here's a regular bar of soap. Drop it in the water. Ready? So regular bar of soap, it sinks. But put the ivory in. Ivory.
Floats.
It's the soap that floats. And so why does it float?
I don't know.
Because there's little pockets of air inside. It's one of those little legends that they whipped it a little bit too long, so there's pockets of air. So if you look over at the microwave, there's a possibility that with those pockets of air, if you kind of look inside, something kind of cool is happening inside. Those pockets of air start to get hot, and that steam that's produced inside, because there's a little bit of water, starts to kind of push out a little bit, and so now it starts to expand. So you see what it's doing inside? It's just getting a little bit bigger and bigger.
Nice.
And at work, if you smell ivory soap coming from the cafeteria, you're going to know that somebody's doing the trick, right? So it's the soap that floats. And they said that they whipped it just a little bit too long, so that's what the legend is. And so what a great kind of marketing ploy. Now, people who have tried it before and said it didn't work, it's because they probably had ivory soap that was sitting in the cupboard for a long, long time. So you need the stuff that's pretty fresh.
Gotcha.
And a microwave works by taking those water molecules and rubbing those water molecules together and heating those up. And so that's why things that have water content will kind of work that way. Ready? I think it's almost done. Oh, it's looking good.
Timing.
Look at that. The souffle is done, kids. Look. Oh, it's soap souffle.
Wow.
Isn't that just
That is
wonderful?
amazing.
Now, I made you some over here as well.
I'm not
just
gonna
so we
touch
have,
the hot
no, it's
stuff.
okay. Because it's not here. Put your hand on top and you can kind of feel. See?
And now
It's solid.
insulating.
See, it's kind of
That's
solid.
crazy. You know, it feels just like if you left this soap suds in your bathtub
Yeah.
and they dried. That's exactly what it feels like. That kind of like crusty stuff.
And so now the question is, what do you do with this? You just take this to the employee bathroom and just set it there instead of the bar of soap. And now you can just chip at it or throw it in the bathroom.
Awesome.
Or whatever it is that you want to do. But we put it up on the website and kind of a fun thing to do with ivory soap and something to know about solids, liquids, and gases.
Yeah.
You know, if you're teaching little science at the same time.
All right, so let's talk about what kind of happened there. So before the microwave, before we put it in the microwave, let me get my stylus out so I can write here. Here we go. Before we put it in the microwave, we had a bar of soap, and if you heard in there, there were pockets of gas. And the gas has gas particles here. So 1, 2, 3, 4, 5, 6, I put 7. Okay, and they have arrows because they're moving around in random directions. Okay, now when we increase the temperature because we put it into the microwave, what happened? So the soap got much bigger. All right, the soap got much bigger. 1, 2, 3, 4, 5, 6, 7. Now we didn't get any more gas into the soap. All right, so we had 7 dots before. We got to have 7 dots after. So the amount of gas stays the same. It didn't pick up more gas. But what happened when we increased temperature? If you remember from the variables notes, temperature makes particles move faster. So how do I show that these particles are now moving faster? I'm going to give them bigger arrows. When I give them bigger arrows, you see that sometimes they bounce off of things, but they need more space to move. They need more space to move, and so they need more volume. So the faster something moves, I'll write this down because it's important. You don't need to put it in your drawing, but faster moving, oh, I'll change that. Faster moving molecules need more room. They need more room to move because they're moving much faster. All right. So now, how could you get pictures here? You can go to let me close that. Insert drawing, and then when you have a drawing here, you can make a bar of soap. That's a square. Boom. And then you can make dots by just choosing shape of a circle. I'm going to make a little dot. Okay, and then I can control C, which is copy, and then control V, 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 and make a bunch of dots. I can make them black, and then I can add arrows by either, you don't even have to really put the arrow on it if you just want to do lines, or here's arrows. There's a bunch of different ways you can do it. All right, so you can do that if you'd like to. You can also, if you find good pictures on the simulation that we're going to do later, you can screenshot. And to screenshot, you put Control and Shift, and then above the 6 on your Chromebook, there's like a box with 2 lines that come after it. And then I can highlight something and it'll screenshot that section for me. So you can insert pictures there. Don't leave it blank though. You got to put something in there if you want your points. All right, conclusion. Why did this happen? As temperature, it increases. Okay, so temperature, let me highlight this to yellow. As temperature increases, the volume increases. So, whoops, I made that one yellow. That's okay. It'll stand. Maybe I'll do red. It'll stand out a little bit more. All right. So as we heat something up or make it warmer, the volume gets bigger. The particles need more space because, and this is what I was saying before, the faster the particles move, the more space they need. Whoopsies, I spelled Ned. Need. Okay, and then I'm going to highlight this, and I'll turn that red so it's easy to find for the grader, which should be me. All right, so now we're going to go to this simulation. All right. Click on the picture. Did that click on ideal? Let me maybe click on ideal. All right, let's see what the other directions. Let's move my head again here. Using the bike pump 3 times to add particles to the container. 1, 2, 3. Okay. Click on the option in the upper right hand corner. Hold pressure constant. Click on the width of the collision counter on the right hand side. Width and collision counter. Okay. Adjust the temperature of the particles in the container as needed. Okay. So right now the temperature is 300 K. Okay. So what is the width? The width is 10 nanometers. The volume, I don't know. I'm gonna say that that's medium right now. I can change that if it doesn't get any smaller, if it doesn't get any bigger. And then pressure is 17.5. And number of collisions. Okay, let's hit this play. And we got 109 wall collisions. Okay, so now I need to cool it down to 200. So cool it down. Whoa. As you can see, as I'm cooling it down, this is shrinking. Okay, now it doesn't have to be exactly 200. I'll try to get it exactly. Oh, got it. All right. So now what's the width? What is that? 6.7 nanometers. I would say that this is definitely smaller. And pressure is still 17.5. Whoopsies. 17.5, and number of collisions, 126. So about the same. I mean, with how many particles are in there and how many times they could collide with the wall, 109 and 126, they're pretty close. Okay, so now I got to heat this up. I want to say it's 400. 400K. Put this on fire, and we can see that it's growing. Okay, 300. Oops, slow it down. Oh, went too much. Perfect. All right. Now it's 13.3 nanometers. Volume, I would say that this is large. Pressure, what do you know? 17.5. And wall collisions. Let's take a look here. 110. So all three of these are pretty close to each other. Okay. Now I'm going to highlight the section I did, and I am going to make that red. There we go. So it stands out for the grader. All right. As temperature increases, volume increases. So as we heated it up, the more space that it needed, and so the volume got bigger. Well, I took it away. Here we go. Red increases. Describe why this relationship occurs using temperature, speed, and the volume of a container. As the temperature increases, the speed of the particles increases. And then I'll say the faster moving particles need more space. I'll put in parentheses, space is volume. Need more space to move. Highlight that. Change that to red. Okay, describe how the number of particles could affect the pressure in this simulation. How the number of particles. Okay, well, the more... Whoa. Let me go back here. Move that down. Okay. Whoop, hit the wrong thing. Sorry, I'm going all over the place here. There we go. All right. The more particles could affect the pressure. Ooh, I think I want to change that. Describe how the number of particles could affect the pressure in the simulation. Well, we talked about pressure briefly in the beginning. I won't pull that slide up, but pressure is the amount of collisions. All right, so the more particles we have in a container, the more likely they will collide with the walls of the container. Uh-oh, frozen. All right. Walls of the container, increasing the pressure. All right, so that's bringing pressure into it. Okay, now we can go to the notes. So I'm going to close this off. I'm going to move this over here. Okay, now let's take a look at the notes here. All right, Charles' law, definition. As temperature increases, volume increases as well, as long as pressure and number remain constant. So if we don't add particles or take particles away from a sample of gas, and as long as we keep the pressure constant, the way we can keep pressure constant is if we have a flexible container. So if we're doing this in a balloon or something that can change its shape or size, like the soap could get bigger or smaller depending on the temperature. It can change its size. It's not rigid like a I would say like a glass container or like a metal like water bottle that's capped. As long as it can keep the pressure and the number of molecules inside constant, if we increase the temperature, the volume will also get bigger. So what does the equation look like? V control comma gets me that little one. I'm going to hit it again to get back to normal. Divided by T, 1. Now, what do they stand for? Volume and temperature in the ones just mean our initial condition, or what they were originally. And that's equal to V2 divided by T2. All right. So our volume divided by our temperature in an initial case is going to be equal to our volume divided by our temperature in a secondary case. Okay, so now what does that look like for our drawing? So here's where I will snapshot it here. So I did Control Shift, and then above the 6 on my Chromebook, the square with the 2 lines. And I'm going to take this drawing, and I am just going to steal it, copy to clipboard, and paste it in there. Okay, now I want to describe this a little bit, what's going on here. Make this nice and big. Okay, so each dot is a particle, and I have 4 to start and I have 4 to end, which is good because we want to keep how many particles we have constant. All right, we don't want to add or lose anything. All right, so I start with these particles. They're moving around. They have these arrows. I increase the temperature, so these arrows get bigger, so they need more space to move, and so this flexible container they're in, it starts to get bigger. It increases the volume. Now let's go to the graph. The graph, you can insert picture, or you can, again, Control Shift, square with 2 lines, boom, copy, paste. All right, so we have a direct relationship where we have a line, and remember, a direct relationship is when both variables do the same thing. So if I increase this temperature, the volume also increases. So if I start at a temperature of 0, I start at a volume of 0. If I increase this temperature to, looks like a 5 here, then this volume gets, I think that's a 10 or something. I can't tell, but at least it gets bigger. I know it gets bigger. If I increase the temperature to, I think this is 10, I increase the volume to a bigger number. They both go up, but the opposite is true. They can both go down as well. So if I make something colder, the space that the gas is in should start to condense or start to get smaller as well. So less temperature, less volume. The next thing I need to do is this practice problem. So let's go through this. An air mattress. Okay, remember how I set this up? I got V. Let's see. Oh, here we go. I got to click on that. There we go. I do V1, T1, V2, T2. And it's important to set it up the way I have it set up here. And that allows us to, like we did in the last one, Avogadro's law, cross multiply here. So we have 25 liters. Liters is a volume. That's what we're starting with. When it was blown up, the temperature was 20 degrees Celsius. Okay, now here's a key component here. Our temperatures have to be in Kelvin. Let's see. I think I may have forgotten that on the slides here. I'll go through and I'll change that quick. All right, so how do we change it to Kelvin? All right, Celsius plus 273 equals Kelvin. Okay, so I'm going to have to make some changes here. So what we're going to take here is 20 plus 273 gets us 293. So 293 Kelvin. All right, so now let me maybe erase this here. All right, let's look at volume 2. Oh, sorry. I didn't read the question. I should have read the question. All right, overnight, the temperature dropped to 15 degrees Celsius. Okay, so now temperature 2 is 15 plus 273 to make sure everything is in Kelvin. And so we get temperature 2 to equal, that would be 88. 288 Kelvin. Find the new volume. Okay, that's what we're looking for here. So how do we find the new volume? Okay, now these numbers that I have up here are not going to be 100% accurate because I forgot to add the 273. I should have done that. Must have been a late night when I was doing notes. All right, so what do we do though? Here's the process. This is the most important thing. How do we solve these problems? First thing we're going to do is cross multiply. Okay, so I'm going to take these two numbers. Oh, I did eraser. That's okay, it still works. I got to cross multiply here, both of these things. So I'm going to get 25 liters times my 288 Kelvin is going to be equal to my 293 Kelvin times my question mark or X or whatever you want to put there. Okay, you can just leave it as volume 2 if you wanted to. All right, now let's solve that one side just to get rid of some numbers. So 25 times 288, 7200 equals 293 Kelvin. Okay, so now how do we, times a question mark. Go to green now. So how do we get that question mark by itself? We need to divide this 293 on both sides. So I'm going to put it here. I'm kind of running out of room. 293 divided by 293. So now 7. Oh, I can just go back. Divided by 293 gives us 24.57. 24.5, whoopsies, 57. And what would that be? That would be liters. That's our volume. Now, just a quick check. Okay, I started at 293 and the temperature went down. If the temperature goes down, then the volume should go down also. Well, I started at 25 and now I'm at 24.5. So it did go down. So that's a check that I was doing it the right way. Now, again, these numbers on the slideshow are not going to match. But I did all this work. So I cross multiplied and then I divided by my temperature 1, my original temperature. And then when I put in the numbers, these numbers don't match, but you should still see that the volume gets less. All right, so now let's 24.57. 24.57 liters. And I'll box that because that should be the correct answer. Now when I scroll, it probably won't stay there. Yeah. Just clear it. Okay, next, find the volume of a balloon if the temperature changed from 325 Kelvin to 298 Kelvin when the original volume. Okay, so I want to set this up the same way that I set up the last one. V1, T1, V2, T2. Okay, that's fine. All right, original, well, I'll go number by number. Temperature changed from 325K, so that's where it started. 325 Kelvin. And it dropped to 298K. Okay, so what that tells me, if the temperature dropped, the volume should drop. Let's check that out. Okay, the original volume was 1.2 liters. So volume 2 should end up being less than 1.2. Now, next step, cross multiply. Boom, boom. So 1.2 times 298 equals 325 times our X, question mark, V2, whatever you want to call it. Okay, what's our next step, Mr. Ziegler? Great question. We're going to divide by 325. Now, you could multiply these two numbers together before you divide. Doesn't really matter. But since I did that last time, I'm going to switch it up here. Divide by 325 because I got 325 on top. On bottom, those cancel, and that gets X by itself. So now let's solve this. Let's solve this problem. 1.2 times 298 divided by 325 should be less than 1.2. It is 1.1. All right, volume 2 equals 1.1 liters. There we go. All right, that's it for the notes. That's it for the worksheet. I hope that helps you understand Charles' law a little bit. There's two more laws that we're going to go through, and if you have questions, make sure that you send me an email. All right, thanks for your time.